Welcome back, everybody, to the afternoon session. So we start with the lecture by David Schaich from University of Liverpool. So David is going to talk about lattice supersymmetric field theories. David, please.
Thanks, Anosh. I think this is a nice way the schedule has been set up today, starting with a bit of lattice field theory, then some holography, and now I get to put both of those together to look at supersymmetric field theories relevant to holography in the framework of lattice field theory. And I'd like to just start off, as I am one of the organizers. I'm not going to thank myself for giving an opportunity to lecture, but I do want to thank all of the local staff here who have had a very hard job over the past 2.5 years. It's been challenging everywhere, but especially for a place like ICTS, as we heard at the start of today, whose a big part of its purpose is hosting these meetings that haven't been able to happen for quite some time. In fact, over the past couple of years was when I initially agreed to give these lectures. And let me just start off by first overcoming the jet lag enough to figure out what I wanted to say about each slide. The overall theme that's going to go through these lectures is that while there are challenges to lattice studies of supersymmetric quantum field theories, those challenges are being overcome, at least in some cases, and overcoming those challenges actually opens up a wide variety of interesting applications and explorations that have really only begun to be explored by the global community, both in continuum theoretical physics and lattice field theory. So I have 3 lectures to tell you about all of these topics over the next 3 days. And all that we'll cover today is this first overall bullet point, looking at motivation for why to talk about supersymmetric lattice field theories, some of the obstacles to that, and a formulation that allows us to make progress. All of this is related to supersymmetry breaking in discrete space-time and ways to get around that. Then, depending on how quickly I get through all of today's material, some of it might spill over to the next lecture on Wednesday. Otherwise, we'll look at some practical applications, actual numerical calculations that have been done, trying to avoid preempting any ongoing work that might be presented in the research talks coming up later in the program. And starting first with what I focus on as a computational lattice field theorist, looking at n=4 super Yang-Mills in 4 dimensions, which we heard a lot about just before lunch, and then going on to generalizations of that to lower dimensions, as well as some quicker looks at things I don't actually work on, in particular n=1 super Yang-Mills in 4 dimensions, which connect to some remaining challenges, including generalizing from super Yang-Mills to supersymmetric versions of QCD with matter multiplets, as well as the issue of potential sign problems in numerical lattice calculations. I'm going to avoid any really detailed calculations and try to focus on the concepts, and I do want to encourage questions and interactions to come as we go through. There's a saying I like from Vicky Weisskopf, was department head at MIT for many years, that it's better to uncover a little than to cover a lot. And I'm going to try to uncover a bit about lattice supersymmetry for you. And maybe in that spirit, just to give me a bit of a guide, I've set up these lectures on the assumptions that most of you are more familiar with supersymmetry in the continuum than with lattice field theory in general and lattice supersymmetry in particular. Could I just get a show of hands about who feels comfortable with supersymmetry in the continuum? And who feels comfortable with lattice field theory in general? So it's about evenly mixed. Is there anyone who feels comfortable with lattice supersymmetry? Yeah, there should be some of whose names will show up soon. So hopefully that will give me some guide to judge how much I pitch and how much I go into detail about some of those different topics of continuum supersymmetry and lattice field theory. I'll also mention that in terms of resources, further reading for this topic. This is something that is still fairly cutting edge and ongoing research, so it doesn't show up in any of the textbooks. And good resources tend to be reviews that go through the published literature, put it in perspective, put it in context, and try to highlight the key developments over the years. And I happened to write the most recent of those about last week, which was actually based on the reduced set of lectures, a 1-hour version of these lectures that I gave at the online program last year that tided us over from the initial program that was going to be canceled, that was going to be held in 2020, had to be canceled. Boiled things down to a 1-hour version of these lectures, then wrote that up in review form in that article, and then tried to expand them for the 3 lectures coming up this week. What I realized while doing that was that I wanted to rearrange things, so I have been rearranging things starting about 4 hours before my flight. So hopefully, at least this first lecture is in shape, the rest will come into shape. I also want to highlight, so there are, of course, lots of references within that review that will answer any questions that come up. Among those, I'll highlight an older one from about 10 years ago that is significantly longer and more detailed, going into the exact lattice supersymmetry that's going to play a big role in especially the lectures today and going into the second one on Wednesday. There will be connections to Anna's lectures. I noticed them as she was speaking this morning, and also probably with Georg, who's lecturing next week, looking at the reductions of these theories to 0+ one-dimensional matrix models, and in particular, numerical simulations with application to gauge gravity duality. And I will try to avoid taking over too much of more recent results that will come in the research talks later in this program. Some of those talks are going to be given by folks like Georg, Raghav. I don't think Anosh is going to speak here, but there are many people who have contributed to the development of lattice supersymmetry over many years, approaching 20 years now since this topic really had a renaissance, starting off from a quiet period. Hopefully I have accounted for a decent representation of that community just in this block. If you notice anyone I'm missing, I'll give these slides an edit before they go online, so feel free to tell me if there are any omissions here. And with all of that out of the way, I will now finally launch into the content, starting with a fairly extensive motivation. As the saying goes, the journey of 1,000 miles begins with asking, is it worth it? So I want to make the case that it is worth spending 3 lectures talking about lattice supersymmetry, with the overarching motivation that lattice field theory can really promise non-perturbative first principles predictions for these strongly coupled supersymmetric quantum field theories that can be applied to many different domains. So let's break this up into 2 pieces and look first, just a very brief review of what Anna was telling us earlier today. How exactly does lattice field theory promise predictions from first principles? So if we formally start off with this expression for an observable, an expectation value, as in terms of the Feynman path integral, in all of these lectures starting now, I will Wick rotate to Euclidean space. So the exponential factor here is just e to the minus action that depends on the generic set of fields in the theory phi. We integrate over all of those field configurations, compute our observable of interest on those field configurations, normalized by the partition function, which is just the integral with no observable in it. And we have the question of how do we evaluate what is formally an infinite dimensional integral? In general, that cannot be done analytically except in very special, very simple integrable systems. And the lattice approach to tackling this question, physics, extracting predictions from a quantum field theory, is to regularize the system by formulating it in a finite discrete space-time in Euclidean signature, which has the advantages compared to things like dimensional regularization or other ways of regularizing integrals that we retain exact gauge of variance in this discrete lattice spacetime. We're not expanding in any small parameter, so this is a fully non-perturbative regularization in contrast to perturbation theory, and we operate directly in 4 dimensions or however many dimensions we may be interested in. We don't have to worry about defining things like gamma 5 away from integer numbers of dimensions. So there are lots of things to like about lattice field theory. Anna will tell you much more about that. I'll turn immediately to focus on some of the drawbacks or the downsides. There's no perfect regularization out there for quantum field theories. They all have their issues. And in the case of lattice field theory, the issue is breaking symmetries, and in particular, the space-time symmetries of the Poincaré group, translations, rotations, and boosts, which do not exist in a discrete space-time. So we take our space-time, we replace it with a bunch of sites that have a constant spacing between them. We'll call that small spacing A, and that small distance scale defines a high energy scale that gives us a UV cutoff that's proportional to 1 over A, the inverse lattice spacing. And we're normalizing the theory. Getting rid of the regularization corresponds to removing that cutoff, taking the lattice spacing to 0, the cutoff to infinity. This is known as the continuum limit. And we have to do this in such a way that the overall lattice spacetime still remains finite. It doesn't all collapse to 0. So if we have some number of sites filling up some distance L in this finite spacetime, we have to keep adding more and more sites as the spacing between them gets smaller and smaller, so that we recover the continuum quantum field theory of interest in this renormalized continuum limit. And so far, this is a lot like a sort of naive hard cutoff regularization that would be the first thing you would see in a quantum field theory course, where you also impose some UV cutoff, you break Lorentz invariance in that way. Lattice field theory, however, is smarter than your average cutoff because the lattice structure, the way in which these space-time points are organized, can actually preserve a discrete subset of those symmetries. So instead of continuous rotations in Euclidean space-time, we have rotations by 90 degrees in each dimension, a hypercubic group of discrete rotations. We have discrete translations, shifting everything by units of the lattice spacing that preserve all of the symmetries. And you can actually show that if your lattice structure has a sufficient amount of symmetry, for example, a hypercubic lattice is sufficient for continuous translations, rotations, and boosts to be automatically recovered in that continuum limit without having to fine-tune any parameters. And this is a result, a story that we will see again when we try to generalize this to the case of lattice field theories supersymmetric lattice field theories, recovering supersymmetries in the continuum limit, even when they're broken in a discrete lattice spacetime. Now, the other half, another advantage of this lattice field theory, formulating things in a finite spacetime, is that our path integral now has a finite number of degrees of freedom to integrate over, which means that we can evaluate these expectation values using finite computers. In particular, with the state of modern supercomputing in the 2020s, it's fairly routine for lattice field theory to evaluate systems with up to, say, 1 billion degrees of freedom, things like 100 lattice sites in every dimension with all of the fields defined at each of those sites. This will correspond to things like having your Dirac operator being represented as, say, a billion by billion matrix. And if you do a little bit of back of the envelope calculations, you'll soon realize that actually storing 1 billion times 1 billion numbers is beyond the capabilities of any computer in existence today, let alone integrating over that many variables exactly. The way that we're able to evaluate these systems with such high dimensionality is by using what's called importance sampling Monte Carlo, and I'm sure we'll say much more about this. I'll just have this one slide saying the basic idea of importance sampling, that we have clever algorithms, I'll leave those for Anna, that sample field configurations proportional to the probability with which they appear in that path integral, proportional to the weight that they have, which is given by that exponential e to the minus s, normalized by the partition function, which requires that the lattice action be a real positive definite number. And we'll come back to that issue later. What happens if that does not hold, and we have what's called a sign problem, where this expression is not straightforward to interpret as a probability. But assuming that our algorithms work, we have a nice real positive lattice action, then the expression for the operator expectation value boils down from that path integral to just summing over measurements of the observable of interest on some number here, n, of independent field configurations, average over all of those measurements, and assuming those field configurations are truly independent, which can be a tricky algorithmic issue, the statistical uncertainty on the result vanishes proportional to 1 over the square root of the number of samples that we are able to generate. That n is just a function of the amount of computing time that we have, which in turn is a function of the amount of money that's available to carry out these calculations. So that is one side of that motivation, how lattice field theory can promise those first principles predictions, in particular through high performance computing. Turning now to supersymmetric quantum field theories specifically, we can think about what strongly coupled phenomena would be interesting to look at with that lattice machinery. So I'll go through a few areas, starting with the topic of potential new physics beyond the standard model. This is a picture of the LHC from back about 10 years ago when it was first getting started. And if you know anything about supersymmetry at the LHC, you'll know that it hasn't been discovered there. And a lot of the simplest supersymmetric extensions of the standard model, things like minimal supergravity at various benchmark points based on perturbative calculations that were done in the 80s and 90s for the most part, those have largely all been ruled out. And any low-scale supersymmetry around the electroweak or TeV scale is going to have to do something more interesting than M-Sugra, or what was in vogue before the LHC came along to rule it out. We could make the case that that is motivation for looking at those supersymmetric extensions of the standard model non-perturbatively, where lattice field theory is a useful application. That may be a bit optimistic to argue. One thing that we can say, however, is that as nature is not supersymmetric, at least up to the electroweak scale, if there is any supersymmetry in shorter distance, higher energy scales, which those of you working on string theory may be comfortable with assuming, that fundamental supersymmetry needs to be broken in some way, going to the longer distances at which we live. And in general, we expect non-perturbative supersymmetry breaking, in particular dynamical supersymmetry breaking, that is the sort of process that we would like to look at through a non-perturbative calculation like lattice field theory. One complication to that side of things is that those dynamical supersymmetry breaking setups tend to involve chiral gauge theories, which pose their own challenges for the lattice that I'm not going to talk about, and I don't think anyone is talking about in this iteration of the program. It's a very long-standing question of how to non-perturbatively regularize chiral gauge theories and define them on the lattice that has not yet been solved. So what may be more interesting than supersymmetric extensions of the standard model is looking at fundamental aspects of quantum field theory, where supersymmetric quantum field theories have for many years been a very important testing bed for all sorts of investigations, ranging from Seiberg duality in N=1 super QCD that has produced results like exact knowledge of the extent of the conformal window, the range of the number of quark flavors for which these supersymmetric theories flow to conformal fixed points in the infrared, as well as the closing of that window, the loss of conformality for different numbers of flavors, as well as, say, some of the initial developments of S-duality. Dualities between strongly and weakly coupled systems were done by Montonen and Olive in the context of maximally supersymmetric Yang mills many years ago. And even now, N=4 super Yang mills plays a big role in things like scattering amplitude calculations and non-perturbative analyses like the Bootstrap program, at least some of which can benefit from non-perturbative lattice methods. The third, and obviously not least, application here is most in line with the spirit of this program, using lattice field theory to look at the supersymmetric CFT side of ADS-CFT duality, probing the holographic dualities that relate those supersymmetric systems to quantum gravity in a higher number of space-time dimensions. So a lot of the work that has been done in that area, and that I'll be talking about probably Wednesday, has been to numerically and non-perturbatively test some of the conjectures arising out of these holographic dualities. Another thing that we could think about is, if we are willing to take holography as certain, then the formulation of supersymmetric quantum field theories on the lattice can actually provide a non-perturbative definition of string theory. I won't have too much more to say about that, but I want to mention it because it was one of the main motivations for that work in the past. This paper by Juan Maldacena came up already earlier today, and it ended with the discussion that one of the nice things about the duality being proposed was precisely giving this definition, at least with some caveats in flat spacetime, in a region of large N limits of field theories, emphasizing that this is a non-perturbative proposal for defining M/string theory, because the field theories, at least in principle, can be defined non-perturbatively. And what this last phrase is referring to is lattice field theory, an in principle non-perturbative definition of, in this case, N=4 supersymmetric Yang mills. So let's turn to that and see how we can take this non-perturbative definition on the field theory side from principle to practice. We immediately start running into some challenges with that related to supersymmetry breaking in discrete spacetime. So I'm going to make the argument that the lattice discretization of spacetime necessarily breaks supersymmetry, and it often does this in several ways. The maybe easiest to look at and appreciate from the outset is by just thinking back to Anna's lectures this morning, where she was telling us about how fermions and scalar fields are identified with the sites in this discrete spacetime, while the gauge fields correspond to gauge connections between those sites, and so are associated with the links in the lattice structure. So this is largely a reminder of what we had this morning. We've discretized spacetime into a bunch of sites. Those sites are connected by links, and from those links we can form closed loops that are gauge invariant objects like plaquettes. So that's the basic ingredients of lattice field theory. And when we have things like gauge fields associated with the links, while the fermions are associated with the sites, what that means is that, say, a gauge field and its superpartner gaugino are going to transform differently under lattice gauge transformations, so that the action of the supersymmetry that connects those different degrees of freedom, relates or transforms gauge fields into gauginos and vice versa, is not going to commute with the gauge invariance in the lattice field theory. We might think that things are a bit better for non-gauge theories, so things like Westhamina models where we just have fermions and scalars. Both of those are typically identified with the sites of the space-time. But even here, there's a complication from that fermion doubling problem that Anna got into toward the end of her lecture today, that in order to deal with fermion doubling and get the desired number of fermions, we have to do some violence to the lattice definition, either staggering them, adding in a Wilson term, putting them on a domain wall, which will come up in Anna's next lecture. And whatever we do to those fermions, if we don't do that to the scalars, then again, there's a related breaking of supersymmetry, a disconnection between those two superpartners from the way that we have defined the theories on the lattice. Now, there is a bit of weasel word of typically here, and the question you might be asking, whoops, I forgot that I had a statement about why this actually matters. Why do we care if we break supersymmetry on the lattice when, to complete the calculation and the renormalization of the system, we're going to take that continuum limit in the end, get rid of the lattice spacing, and get back to a continuum theory? Does it matter that we are breaking supersymmetry? It does, and it matters because when we're doing a quantum field theory calculation, if we don't have symmetries to protect our calculation from various certain, in this case, supersymmetry violating operators, those operators will be generated by quantum effects, and some number of them tend to be relevant operators in the renormalization group sense, or in the practical sense that the coefficients of those relevant operators would have to be fine-tuned by hand in order to reach the correct continuum limit as we take the lattice spacing closer together, lift the cutoff to higher energies. This is especially severe in supersymmetric theories that include scalar particles, so extended super Yang-Mills or super QCD that has squarks in matter multiplets. You know, the mass of those scalars presents a fine-tuning challenge similar to the mass of the Higgs boson in the Standard Model, just a scalar mass that would be generated in the absence of supersymmetry and would then have to be fine-tuned to reach the continuum limit. That is probably the single hardest of these SUSY violating operators to deal with, but there is a whole zoo more of them, things like Yukawa couplings between those scalars and the fermions in the system. Those fermions, either quarks or gauginos, pick up mass terms of their own that have to be fine-tuned away to get back to the supersymmetric system. And there's also several different four scalar terms that typically arise depending on the theory with different transformation properties under global symmetries. So you pick up multiple SUSY violating operators, each of which has its own parameter to be fine-tuned. If you do careful counting, there's often 10 or more of these parameters. So trying to imagine a 10-dimensional parameter space that a calculation would have to wend its way through to find the appropriate point corresponding to the target supersymmetric quantum field theory. In principle, that can be done if we had infinite computers and infinite grad students to run them. But in practice, it's not realistic to do and not really worth pursuing in the first place. And this is part of the reason that lattice supersymmetry languished in the broader lattice field theory community for many years throughout most of the 80s and 90s. There was very little work done on it for this issue. And we've seen this one way one way to appreciate supersymmetry breaking in a lattice theory. I was anticipating the next slide, which pointed out that there are these weasel words talking about the typical situation. And you might be wondering, are there special cases, or are there clever things we could do to avoid the typical and get a better result? So a question that could be posed, if some lattice field theorists were sufficiently clever to come up with a lattice discretization that could match on fermions to the links so that they transform in the same way as their gauge boson partners, or similarly discretize the scalars and fermions in the same way, would that solve the problem? The answer is no. And this is sort of showing that the issue with supersymmetry in discrete spacetime is not so much an issue of practice, what discretization do we choose to implement? It's really one of principle. And in particular, the principle that supersymmetry is a space-time symmetry. It's extending that Poincare group of translations, rotations, and boosts by adding these spinor generators. So I'm going to call them Q and Q bar with an index I going from 1 to a calligraphic N. Those spinor generators are the generators of supersymmetry transformations. There is a whole super Poincare algebra with both commutators and anti-commutators. I'll avoid going through the whole thing, but just highlight this particular set of anti-commutation relations between these supercharges Q and Q bar. So anti-commutating a Q with a Q bar gives us the momentum operator, the generator of infinitesimal translations. And we started off by noting that those infinitesimal translations don't exist in discrete spacetime. We just have discrete translations by units of the lattice spacing. This algebra is broken, and so is supersymmetry, no matter what clever discretization scheme we try to come up with to address the initial thinking about defining supersymmetric theories on the lattice. Now, of course, this is something that was realized even in the first work on lattice supersymmetry. It was by Dundee and Nicholson, or Dundee and Nicolai, sorry, Nicolai, 1977. They raised this objection and tried to think about what could be done about this. And there were some explorations by those folks, Nicolai, by Preskill, by Tom Banks in the early 80s, probably before many of you were born. Some things were tried, none of them really worked so well. One explored by Polchinski and Tom Banks and Windy was to think about a Hamiltonian formulation of the system. So this is a slight variation on the usual field theory setup, where instead of discretizing space and time on an equal footing, we discretize all the space directions in that way, but we keep time continuous, and we work with the Hamiltonian that evolves in continuous time rather than the Lagrangian formulation based on the Feynman path integral and the action. And if we have continuous time, then the generator of translations in time, the zeroth component of P mu, which is just the Hamiltonian, is preserved. And there is a corresponding subset of the supersymmetries who anti-commutate to give that time translations that can also be preserved as well. And preserving a subset of the supersymmetries, going back to that story about preserving the discrete subgroup of rotations, we could hope that that improved the whole situation of taking the continuum limit. We will see that this can happen. In this case, another problem arises that if we want to think about relativistic quantum field theories with supersymmetry, we would now need to fine-tune to recover that Lorentz symmetry, Lorentz invariance of the continuum limit. So we've this approach from the early 80s traded off some fine-tuning of the supersymmetries and ended up being hit just as hard by fine-tuning, for instance, the speed of light in order to get space and time back on an equal footing after discretizing one but not the other. Yes, please.
Why doesn't this problem also occur for just non-supersymmetric cases, where if you just break the limits in weight, some relevant operator?
I would say it does. Yeah, if you want to get a Lorentz invariant theory, maybe I'll repeat the question for those on Zoom. It was, isn't this issue of recovering Lorentz invariance in the Hamiltonian formulation a challenge for non-supersymmetric theories? And it is, and that's why lattice field theory mostly operates with that Lagrangian formulation based on the Feynman path integral. Rich is about to object because there are things you can do. Oh, you're going to elaborate.
Mic is not on.
Yeah.
Oh, yeah. Oh, sorry. Yeah, I mean, the speed of light is just a parameter, and you measure it, and you have the answer. That's not a big deal. The question is, do you get a relativistic dispersion relation? Do you get E equals P squared plus M squared in any speed of light, okay? So you might not get back, and there are spin systems where sometimes you get a non-relativistic dispersion relation. In other cases, you get a relativistic. So I mean, that's the real issue, is do you get back a relativistic spectrum, you know?
Yeah, I mentioned the speed of light as an illustration of kind of things that can go wrong, but
it's a parameter you measure.
yeah, it is harder than that.
As long as it's a constant, you find it.
And I think we will be hearing a bit about this in some of the later talks in the program, in particular, the ones looking at quantum computing.
That's right, quantum computing.
That tend to use the Hamiltonian formulation, especially in quantum simulation, where you want the actual physical time evolution of the simulator to be the time evolution of the system interested in. So a lot of quantum computing is applied to non-relativistic systems where we don't care so much about Lorentz invariance. But yeah, it is a big problem, and it's the problem that you hit if you try to take this approach to preserving part of the supersymmetry with this eye on the super Poincare algebra. And if there are no further questions, I'll move on to even a third and possibly more fundamental difficulty with supersymmetry in discrete space-time. So it's obviously related to the issue of the super Poincare algebra. And it has to do with the Leibniz rule, or the product rule of derivative operators, where we're all used to the derivative of the product of two functions or two fields being the sum of the derivative acting on one multiplied by the other function. That's the Leibniz rule, and it plays an important role in demonstrating that systems are supersymmetric. So if we think about, this is motivated by going back to that story that even though we don't have infinitesimal translations, we do have finite translations in lattice spacetimes. So the derivative operator corresponding to the momenta gets replaced with the finite difference operator. Anna showed exactly this forward difference operator in her lectures this morning. The question is, can we come up with some discrete analog of supersymmetry that would generate finite translations rather than infinitesimal ones? The easiest way to see that that is not possible is by thinking about the Leibniz rule, because that does not hold for these finite difference operators. If I just plug in the definition of the finite difference on the product of two fields, I have to shift both of those fields at once, and then subtract the unshifted product. And if I break that up into products of the finite difference acting on one and the other, there are additional terms with the fields at different sites that then have to be canceled in this way, with an additional term that comes in with a factor of that non-zero lattice spacing. So this causes problems if we're trying to show that a theory is supersymmetric by looking at the supersymmetry variation of its action. So in the case of quantum mechanics, a supersymmetric quantum mechanics that has some scalar degree of freedom, it's not really a field, scalar phi, it has two supersymmetries relating that phi to two fermions, psi 1 and psi 2. I'll skip the actual calculation and just give the result that the variation of that action has the form of the Hamiltonian, the time translation operator, acting on each of those fields separately, where this W is a function of the scalar variable, known as the superpotential, that defines a class of supersymmetric quantum mechanics theories, depending on the superpotential. And if our time derivative obeys the Leibniz rule, then these two terms can be combined into an overall derivative that is being integrated over, and with an appropriate choice of boundary conditions. For instance, on the lattice, we'll usually impose periodic boundary conditions. We then obtain a manifestly supersymmetric system by integrating that full derivative, which we can't get when there are these extra terms lying around in what would be the full finite difference of those two terms. Now, that was one simple example for this particular finite difference operator. I think Anna gave you the homework problem of thinking about different finite difference operators that bring in multiple different nearest neighbor terms or next to nearest neighbor terms. There's a whole zoo of different operators that we can construct, which generally approach the same infinitesimal version in the continuum limit. And it's possible to prove that the Leibniz rule doesn't actually hold not just for that forward difference, but for any local finite difference operator at a non-zero lattice spacing. And more than 10 years ago now, there were some so-called no-go theorems that were proven to show that if you have a finite difference operator that gives you the Leibniz rule to provide a supersymmetric system, it has to be necessarily non-local. And I won't say anything more about those theorems or their proofs other than that they are out there, and Georg Bergner will be joining us a bit later in the program when he's able to. He may be the best person to talk to about those if you're curious. Since that time, and even before, there have been sort of ongoing efforts to try to strike a balance between the locality of the finite difference operator that feeds into the locality of the quantum field theory itself and the amount of supersymmetry that can be preserved on the lattice. So I think I'm going to give references here just because I'm not going to go into any details about these. Just flag them as ideas you can look into if you're interested. There's a construction at Daisuke Kado, and others have worked on, called a cyclic Leibniz rule, that is able to preserve a part of the lattice supersymmetry, at least in quantum mechanical systems rather than true quantum field theories. Alessandro Dada and others have also developed a product operator that is not ultra-local, but maybe local in the continuum limit, that gives that full lattice Leibniz rule at the cost of gauge invariance and some other issues. But these are complicated constructions that tend only to be applicable to some of those special cases like quantum mechanics and systems without gauge invariance. So going forward, I'll just be completely sacrificing supersymmetry in this supersymmetry versus locality balance, keeping everything ultra local as simply as possible and trying to figure out what we can do with that supersymmetry breaking. So that was the first topic, going into why we're interested in lattice field theory and the problems that arise. So I'll just pause briefly if there are questions about that before going into the next topic and showing how the supersymmetry breaking can be at least ameliorated in discrete space-time. And not seeing questions here, and not actually seeing Zoom at all. So hopefully that's running elsewhere. I'll go ahead to the next big topic for the rest of today's lecture, which is that although supersymmetry does have to be broken in discrete spacetime, if we have multiple supersymmetries, it is possible to break only some of them and preserve a subset, and in particular, preserving a closed subalgebra of that full supersymmetry subalgebra, even in discrete spacetime. This will have the benefit of ensuring the correct continuum limits with far less fine-tuning than those order 10 parameters that we were going through earlier in the case when everything was broken. Now, over the years, there were two main ways of developing this way of reformulating the theories in a supersymmetric way. One coming from so-called topological twisting, the other coming from orbifolded dimensional deconstruction. And that review that I mentioned at the start is really focused on that whole story and the eventual conclusion that those two different ways of approaching the question, although they use some very different concepts and very different language, end up producing exactly equivalent lattice constructions. Orbifolding was the initial approach investigated by folks like Andy Cohen, David Kaplan, Mitat Unzel, and Ami Katz. I'm going to actually not say anything about it. I'll rely on the fact that the resulting construction is equivalent, and I'll tell you just about this twisting approach that I find a lot easier to follow because it actually breaks up the construction into two independent steps. First, we will reformulate a continuum quantum field theory in terms of twisted degrees of freedom. We'll go through that twisting procedure, and then we will take that reformulated continuum quantum field theory and discretize it on the lattice, whereas orbifolding, that approach requires that those two steps be done simultaneously, getting the reformulated system necessarily through this latticization of an extra dimension. One limitation, or maybe I'll just call it a feature, of all of these approaches is that they only work if there's a sufficient amount of supersymmetry, and I can tell you upfront what sufficient means, that if we're working with a supersymmetric theory, such as Super-Yang-Mills in d dimensions, we would need to have at least 2 to the power d supersymmetries in order to go through either of these procedures. So in 4 dimensions, that picks out the unique case of n equal 4 Super-Yang-Mills. There are more possibilities in 2 and 3 dimensions. And what I'm going to do is actually go through that full 4-dimensional case and save the lower dimensional stuff for somewhat a generalization or a dimensional reduction of the result that comes out of this full consideration of n equal 4 Super-Yang-Mills. So there were not so many hands that came up when I asked about comfort with supersymmetry in the continuum. So I'll repeat a bit of what David was saying before lunch about what is n equal 4 Super-Yang-Mills and what are the basic ingredients of it. This is very useful, obviously, for that S duality, for ADS-CFT, and all sorts of other investigations in modern theoretical physics. And there's a sense in which its broad use and applicability is a consequence of n equal 4 being arguably the simplest non-trivial quantum field theory that we can have in 4 dimensions, in flat space without gravity. So what it is, we start off with an SUN gauge theory, and we're going to have the n equal 4 Majorana fermions, I'll call them psi, and then there are 6 scalars, phi ij, all of which are massless and transform in the adjoint representation. And that masslessness and the transformations are a result of the supersymmetries that relate all of these fields together. I see there's a typo on here where all of those omegas are meant to be Qs. The supersymmetry is acting on, say, a state with helicity 1, so a component of that gauge boson. This is adapted from the modern supersymmetry textbook by John Turning. And given the typo, I'll go through it pretty quickly. We act with that lowering, the supersymmetry Qi as a lowering operator on that helicity 1 state. We get something with helicity 1/2, which we can recognize as part of the gaugino corresponding to that gauge field. If we act twice, because these supercharges are fermionic, we pick up the antisymmetric representation, so the 6 scalars, and then acting 3 and 4 times gives us the remainder of the fermions in the gauge boson, all of which are then transforming in that same supermultiplet. That's why they all have to be in the same representation and all massless. So the action that we have for this theory is going to have no mass terms, but all the usual kinetic terms.
Sorry, David, one question. Previous slide. So these numbers 1, 1/2, 0, what are they?
That's the helicity of that state that corresponds to either a gauge boson, fermion, or scalar. So we know that the gauge boson has those 2 helicity states, left and right circular polarization.
Okay.
That's what those are. Similarly, the 2 chirales for the fermions. This would make more sense if I didn't have that typo from copying and pasting in there.
All right. Yeah, thanks.
But that is how this gauge supermultiplet is built from the 16 supersymmetries of n equal 4 super Yang mills to define define the field content of the theory, and then the action that it's obeying with Yukawa and quartic terms, along with the kinetic terms, actually has only a single coupling. All of the coefficients of those terms are related by those supersymmetries, and the global R symmetry, that is that index I refers to transformations under this global R symmetry. So that the only parameter that we end up with is the Tufts coupling, so the Yang-Mills gauge coupling squared times the number of colors n. So n and lambda end up the 2 parameters that characterize n equal 4 super Yang-Mills. And this is also, as we saw, a conformal theory with a beta function that exactly vanishes for any value of the coupling. So it's really a line of conformal fixed points going from 0 coupling on off to infinity. And starting with this system, the main idea of this topological twisting approach can be appreciated by this sort of intuitive picture that I like, which is to take those 16 supercharges and organize them into a 4x4 matrix, whereas we go across each row in the matrix, we increment the R index on the supersymmetries. And as we go down each column, we're varying the space-time indices, so the Lorentz index that has been Wick rotated to Euclidean time. And we take this 4x4 matrix, and as a knee-jerk reaction, we expand it in a basis of gamma matrices, so going from 4 times 4 to 1 plus 4 plus 6 plus 4 plus 1 supersymmetries. And given the role of the R symmetry and the Lorentz index along each row and column of this matrix, we can recognize that picture of expanding a matrix in a basis of gamma matrices as organizing these supercharges in representations of the so-called twisted rotation group. So it's the diagonal subproduct, this diagonal subgroup of the product of that SO4 group of rotations, the Lorentz symmetry in Euclidean spacetime, and then an SO4 subgroup of the full SO6 R symmetry. And I'm using SU4 and SO6 interchangeably for the R symmetry. That the double cover is not going to be relevant for anything we see here. And at least as long as we are in flat space, this is just a change of variables. We have exactly the same n=4 super Yang-Mills system, but now we have 16 supercharges that, rather than being spinors, are transforming with integer spins under this twisted rotation group. So that object with no index is a twisted scalar supersymmetry. With one index, it is a twisted vector supersymmetry. All of these so-called P forms are completely anti-symmetric in all of their indices if there's more than one. So this is that two-index anti-symmetric tensor representation of the twisted rotation group. And there is an obvious subalgebra of the supersymmetries that can be preserved when they are expressed in this way, which is to take the anticommutator of the twisted scalar supersymmetry with itself. That just gives us the supersymmetry squared, which vanishes. And it looks like there's a question in the front row.
Yes, there's also the Q bar. That's also scalar. You preserve one or two
So
symmetries.
that's a little bit more complicated. That's more like a pseudoscalar. And this is, what do I want to say about these guys? I know where we're going to end up, and in the final construction, we're actually not able to preserve the Q bar itself. At this point, it looks like you might be able to. I agree there, and we will see when we go to the other fields, what comes along to interfere with that and leave us with only that single twisted scalar supersymmetry as the one that can be preserved on the lattice. So at the moment, we are in the continuum where we do have those two nilpotent scalar operators. It's only this one that, when we go to discrete space-time, will remain. We'll see how close I get in the remaining 15 minutes. And what I want to do with this illustration is give, again, the intuitive way of thinking about what's going on here with this twisting is that recalling the anti-commutators of the supercharges were giving us infinitesimal translations in space-time. What we've effectively managed to do with this approach is find a linear combination of those supersymmetries whose anti-commutator is generating a linear combination of infinitesimal rotations that circles back around to its starting point. And that starting point can then be identified with a lattice site and remains infinitesimal without having to translate any distance. So that can be preserved on the lattice, which we will get to maybe not today and maybe on Wednesday. We have a bit of work to do left still with the formulation of the continuum twisted theory, getting the fields in the same formulation that matches what we've done to the supercharges themselves. The fermions are the easy part of this because they just break up into 1 + 4 + 6 + 4 + 1 degrees of freedom in exactly the same way as the 16 supercharges. And yes, we have now gotten rid of all of the spinors in this system, which those in the audience working on lattice field theory will appreciate. As Anna was saying, the spinors are the challenge, they don't play so nicely with the lattice discretization. So it's already promising to have a formulation of this system with only integer spin objects and without spinors. Because the twisting involves just that SO4 subgroup of the full SO6 R symmetry, it's a bit less obvious what to do with those scalars that transform in the 6-component vector representation of that SO6. If we pick out any SO4 subgroup of that, then we end up with a 4-component vector with 2 scalars left over in terms of the R transformations. So 2 singlets, I should call them, rather than scalars. I'll try to reserve scalars for space-time transformations. And the trick that was figured out was to organize these 6 scalars and the 4 components of the gauge field into 5-component complexified gauge fields in this way, so that A mu are the 4 components of the gauge field. We have the B mu are the 4 scalars that transform as a vector under SO4R, and then the 5th component of these complexified gauge fields A and A bar are filled by the remaining scalars phi and phi bar. It's not obvious to look at it why we would do this or how people came up with it. It's a bit easier to see if we actually think about the system in 5 dimensions, still with 16 supercharges. If we go through the twisting procedure in 5 dimensions, we have the advantage that the 5 components of the gauge field match the 5 scalars that we have from dimensional reduction of n equal 1 super Yang mills in 10 dimensions. So under the twisted decomposition that gives us that SO5 twisted rotation group, it's easy to see that both the gauge field and the scalars are transforming as twisted vectors. And the complexified gauge lengths, similarly for the A bars that I've omitted here, have a simpler form that upon dimensional reduction to get us back to 4 dimensions, just project out the 5th component of each of those A sub A and phi sub A as those 2 scalars that were looking a little awkward when we were formulating things just in 4 dimensions. So that's a kind of slick way to motivate that treatment of the bosonic fields, packing them together into these 5-component complexified gauge fields. One consequence of this is that our initial SUN gauge theory is necessarily promoted to a full UN, bringing in a U1 factor due to that complexification. Doesn't really matter much in the continuum. It will matter on the lattice. We will talk a lot about that on Wednesday. And getting back to maybe the initial considerations of supersymmetry that we had, we also have to think about how to package or represent the fermions so that they manifestly match up as superpartners of these bosonic fields. So the next step here is to take some of those representations of the twisted rotation group and package them together themselves into, say, a 5-component psi A that brings in a twisted vector and that pseudoscalar eta bar. Similarly for the corresponding supercharges, and then there is a 10-component antisymmetric tensor with A and B running from 1 to 5 that packages the 6 plus 4 twisted tensor and pseudo vector for both the fermion fields and the supercharges. And with all of this expressed in this way, it becomes fairly straightforward to check that twisted scalar supersymmetry that's left out of now those 5 and 10 component packages is now correctly interchanging the bosonic and fermionic degrees of freedom and squaring to 0 when acting upon anything. So acting on the gauge field, we get that 5-component fermion. Acting again, it vanishes. The supersymmetry transformation of the 10-component tensor fermion gives the negative field strength of the A bar gauge field, and acting again annihilates all of that. Acting on the remaining twisted scalar fermion gives a bosonic auxiliary field which has these degrees of motion that can be put in, and again, acting again with the supersymmetry gives us 0. So in general, that supersymmetry is still nilpotent and squaring to 0. So we have now repackaged all of the fields and expressed in terms of these fields the action for the continuum theory breaks up into 2 pieces. So I've made them sort of green and red here. The first piece is so-called Q exact. It is that scalar supersymmetry acting on a fermionic operator that we could push through and expand to explicitly pull out, say that field F bar for the kinetic term of the gauge fields and so on. I'll leave it in this term for now. There's an additional Q closed term that shows up in this action. So with a 5-component epsilon tensor that completely anti-symmetrizes the A gauge covariant derivative, depending on the A bar fields, acting on one of the tensor fermions and contracted with another tensor fermion. And if we want to verify that this action is exactly supersymmetric with Q acting on the action giving us 0, well, in the Q exact pieces, that's fairly trivial because Q squared is 0 always. And then the last piece acting with Q will give us a F bar that includes additional gauge covariant derivatives that are completely anti-symmetrized by the epsilon tensor. So there's a Jacobi identity that is 0 as well. And the action is manifestly supersymmetric in this twisted notation. And I'm thinking how much further I will be able to get today and how much I want to.
David, regarding Q bar
Yeah.
that David asked, if you go back, this slide, I think for Q bar, it is not gauge invariant on the lattice, right? This may open up that Q closed term, and Q bar acts on that. It will become gauge non-invariant, I think.
Yeah, that may well be the case. Again, when we go to the lattice and this, we will no longer have that Jacobi identity. It becomes more complicated on the lattice, but that is a good preview of that. That's a good way of thinking about it. I was getting stuck in the other ways of twisting N=4 super-Yang mills. So the experts in the audience may know that there are 3 inequivalent twists that can be done that correspond to assigning the fields to different representations of that twisted rotation group. And there are things that the other 2 twists also have problems with lattice discretization in that case, because they have to impose a self-duality condition that becomes problematic on the lattice. So it is just this one twist, the so-called Marcus twist, or sometimes now called geometric Langland's twist, is the only one where this procedure carries over from the continuum to the lattice. So I said there were, twisting is nice compared to that orbifolded dimensional deconstruction because there are these 2 conceptual steps we can split the work up into. First, the one of building this twisted formulation for the fields for the action. And then the second step is discretizing that onto the lattice. And that it becomes almost trivial, at least in appearance. The lattice theory looks nearly the same, despite breaking all of the supersymmetries except for that twisted scalar one. So the Q bar that is packaged into the QA now is being broken by the lattice discretization, as is all of those 10 QABs. All that we have to do is take those gauge covariant derivatives, replace them by finite difference operators that depend on the gauge field. in a similar way to what Anna was talking about this morning, so that those complexified gauge fields are replaced by gauge links that are still transforming in the algebra. Yeah. So those U and U bar, as I will call them, are elements of GLNC. And I think I'm going to wind down this lecture on this slide and pick up here tomorrow, just with a few comments about how this differs from what lattice field theorists would be used to. So usually in lattice QCD, for instance, the gauge fields are turned into gauge links, gauge connections that actually exponentiate the degrees of freedom in the algebra and give variables that live in the group. That is not appropriate in this case because we want to preserve the good behavior of this twisted scalar supersymmetry and ensure that both sides of this equality, well, are equal, behave the same way. So the gauge links have to remain in the algebra in contrast to, say, lattice QCD. It also has implications for the measure that we use in the path integral when integrating over all of these degrees of freedom. With links in the group, lattice QCD, you use what's called a Haar measure that is explicitly gauge invariant. Here, we are using a flat measure, which is only gauge invariant because we've complexified the gauge fields and we have equivalent integrations over both U and U bar, those two links. If we do a gauge transformation to the system, U and U bar will pick up transformations, pick up Jacobians in the measure that exactly cancel. And it's only because of that complexification that we are able to have these gauge links in the algebra so that the twisted scalar supersymmetry continues to behave correctly. And one other wrinkle is that in order to recover the appropriate covariant derivatives in the continuum, this is actually almost the same as one of the homework questions that Anna assigned this morning. You can, when expanding the plaquette in lattice QCD with gauge links in the group, expanding an exponential gives you a unit matrix out front. When we have the gauge links in the algebra like we do here, we will actually have to impose that as we approach the continuum limit, we have gauge links that are fluctuating about the identity. We have to pick out that point in the moduli space to get the correct continuum limit. We will revisit that issue when we get to practical numerical calculations on Wednesday. And then the lattice action has exactly the same form as the continuum one, just with that gauge link there instead of the continuum gauge field. And this is where it remains supersymmetric. So Q acting on lattice action continues to vanish. Q squared still vanishes. That's the trivial one. This is the tricky bit where the different finite difference operators, so in that F bar and the D bar, now that we are on the lattice, those finite difference operators are shifting or are connecting different lattice sites within this term. And it's non-trivial, or at least less trivial, to see that there is a Bianchi identity that guarantees that the supersymmetry variation of this term still vanishes thanks to summing over all of the link paths that show up between those nearest neighbor lattice sites in this completely anti-symmetrized sum. And this is where I think that Q bar goes wrong, as Anosh was saying and David was asking. And I think that is also, a good place to wrap up for today and leave some time for final questions, even with anticipation of some dedicated question time later on after Martin's next lecture.
Okay, thanks, David. Time for questions. Navdeep?
I can ask and I can repeat.
So after twisting, we had that eta bar. The only reason to combine eta bars and to get rid of that from the picture is just because we need them to behave similar to scalars, and we don't want q bar in the picture.
Yeah, this is all notation and changing variables. So in a sense, that eta bar and q bar are still there. They're just wrapped up and repackaged in a different notation that allows us to see that there is this supersymmetry is holding, and in particular continues to hold in discrete space-time. So it's in anticipation of going to the lattice system that we package things in this way. We haven't really gotten rid of the eta bar so much as hidden it within these 5 component objects that we now have to deal with. So all of the 16 supersymmetries are still there. 15 are broken on the lattice. But the fact that it was the particular way we are combining them is to some extent an accident of what we have to do in order to make the supersymmetry manifest once we've set up those complexified gauge fields motivated by that dimensional reduction.
Thank you.
More questions? David.
So we usually think of the index as being on the link for a single index, right?
Yeah.
So
That is in
am I
fact-
supposed to think about chi-AB that has 2 indices? Is that a phase?
Yeah, that's my next slide where I ran out of time. So there's a preview. I call it a plaquette variable. And yeah, since there are some questions, I can just do this slide as an answer to that question because it's the natural next thing to present, or at least I think so. That in this lattice action, in order to have gauge invariance, we need everything to be a trace over a closed loop in the lattice structure. So the indices that we have here are now telling us how they're giving a geometric interpretation of those symmetry transformation properties. So objects with no indices, like that twisted scalar supersymmetry, are identified with the site, which is to say that under a gauge transformation, G, they transform in the adjoint with a G and a G dagger on the same site, whereas those link variables, both the gauge link and its fermion partner psi A, transform with one gauge transformation identified at a neighboring site, n plus u sub A, and the other gauge transformation at the site n. And exactly which side is which differs for u and u bar, and could in principle differ for these chi-ABs as well. What the 2 indices mean is that we now have sort of 2 hops in the gauge transformation. So when we start looking at terms in the lattice action, we will have to verify that they do form a closed loop in the space-time of the lattice, so that upon tracing over them, the gauge transformations G and G dagger cancel out, and I'll start with that on Wednesday.
Okay, so participants on Zoom, any questions? Seems like there are no questions from there. So let's thank David.